Welcome back. In this session, we'll start with some simple FIR filters. Let's start. So, first, let's see the impulse response of a low pass FIR filter. So, impulse response of a low pass FIR filter. Now, we can write the impulse response of this is like say 1, 1, and let me see there's a coefficient that's 1 by 4. So this is a very simple FIR low pass filter. Now let me prove to you that this is indeed a low pass filter, right? So let's do that. Now first I'll obtain the Z transform. So H of Z will be summation m running from minus infinity x of m 0 to minus n, and since this is non-zero 0 to 1, rest of the values are 0, so substituting the values of x of 0 and x of 1, we'll have x of 0, 0 is power 0, x of 1, 0 is power minus 1. Then substituting the value of x of 0 and x of 1, so let's x of 0 is 1 by 2, 0 is power 0 is 1, this is 1 by 2, 0 is power minus 1. So we can write it like this, 1 plus d, and my aim is to prove to you that h of z is equal to 1 by 2 1 minus the transfer function like this, or the impulse response like this is a low pass FIR filter. Now it is a FIR filter. How? Because the impulse response is of finite duration, and let's prove whether this is really a low pass or not. Let's do that. So first let me obtain the frequency response, or simply the discrete time Fourier transform of this. Now discrete time Fourier transform can be obtained from Z transform if we put Z is equal to E is for G omega. So substituting this, the H of Z will be equal to H of omega now. That's 1 by 2, 1 plus e to the power of minus G omega. Right? Alright. So let's see whether this is a low pass filter or high pass filter. Now we know omega in discrete time varies from 0 to pi, or from minus pi to pi. Alright, so let's take the positive frequency value. Let's say the frequency varies from 0 to pi. Alright, so what should happen at omega? This should pass the low frequency. This is the low frequency, and omega is equal to pi is the highest frequency. We have already proved this. This is the highest frequency in discrete time, right? So let's substitute these two frequency values. Let's see what will happen to this filter response. So h of omega when omega is equal to 0 is equal to 1 by 2, 1 plus e raised power 0. E raised power 0 is 1, so this is 1 by 2, 1 plus 1, and indeed this is equal to 2 by 2, that's equal to 1. So this gives a magnitude equal to 1. In other words, this filter will pass omega equal to 0. Now, when omega equal to pi, so when omega equal to omega is equal to pi, what will happen to h of omega? This will be 1 by 2, 1 plus e raised power minus j pi, and if you remember, e raised power minus j pi is minus 1 by 2 minus 1. So this rejects or does not allow the higher frequencies to pass. The highest discrete time frequency is pi. Alright. So this is allowing the omega equal to 0, which is low frequency, to pass, but rejecting the high frequency. Alright. Let me also show you the frequency response with respect to omega. Let me show you that. How I can simplify this here. We can write it e raised power minus j omega by 2. We have already done this. So this will be e raised power j omega by 2 plus e raised power minus j omega by 2. Then writing this 2 here. So I'm writing j. Sorry, this is the marker. So this will be e raised power minus j omega by 2 cos of omega by 2, because e raised power g theta plus e raised power minus g theta. The other two is cos theta. Right? Now plot this. Can you plot this? Let me write it at the so the h of omega is e raised power minus j omega by 2 cos of omega by 2. Now the magnitude of this, the magnitude of this will be, we already done this, the magnitude of this cos of omega by 2. Alright, now we can obtain the magnitude of these two is simply the product of the individual magnitudes, right? So this is equal to 1. So this is cos of omega by 2, magnitude of cos omega by 2. Let's plot it. So let's plot this magnitude response. So this is h of omega magnitude. So the highest frequency is I, right? So this is omega. This is our highest frequency. This is the lowest frequency. Now you can see we know the cos function has the highest value at omega when when theta is 0. So we say this will decrease like this, and when omega becomes equal to pi, this will be cos pi by 2. So at pi by 2 it will be 0. Same thing you can repeat for the negative side. You can say this is minus 1. So this is indeed, this looks indeed a low pass filter response because at omega equal to 0 the response magnitude is 1 and then it rolls off or decreases. So this is indeed a low pass. Now one another important property of the FIR filters is the linear phase. Now the phase here is, you can say phase here is minus omega by 2. We have already plotted this in MATLAB. Please try it again. Use f plot. You remember f plot function to plot this phase magnitude. Let's do this. You will get this response. Right? All right. We have already done this. Now indeed this proves that this is a low pass filter. Now see, we checked the what was the Fourier transform or discrete time Fourier transform here. This is the discrete time Fourier transform of the given filter. Now this is also given in terms of h of z is 1 by 2 1 plus z is 1 minus 1. So this is the transfer function in omega domain, and this is the transfer function in z domain. Now we know the highest frequency in omega domain is equal to pi. This is the highest frequency, and omega equal to 0 is the lowest frequency. Now what does omega equal to 0 and omega equal to pi correspond in z? We know the relationship between z and omega is like this. So when omega equal to 0, z is equal to 1. Right? So when omega equal to 0, z will be equal to 1 from this. Similarly, when omega equal to 0, sorry, pi, not 0, omega equal to pi, z will be equal to minus 1. So lowest frequency in z corresponds to lowest frequency, which is also called omega equal to 0, corresponds to z equal to 1, and highest frequency in z is when omega is equal to pi, corresponds to z equal to minus 1. Alright, so we could have checked this in z domain as well. Right? Now the low pass. Now let's try it for the high pass filter. High pass FIR filter. And these are simple examples. High pass. This is an FIR filter. Okay, this is an FIR filter. Now the impulse response of an FIR high pass. Very simple example is 1 by 2, 1 comma minus. This is a very simple example. Right? Alright. So this is the impulse response of this filter. Alright. So we can obtain h of z. Can you do that? Please try that. This will be 1 by 2, 1 plus, I'm sorry, this will be minus now. 1 minus 0 minus 1. This is the transfer function of this impulse response in z domain. Substituting in this expression, substituting here, we'll get the answer. Right? So this is the. Now let's check the low pass and high pass response. Means if the omega is 0, what do we mean by that? Means when z is 1. 1. What is the value of this? This is 1 minus 1. This will be equal to 0. So this is rejecting low frequencies because omega z equals 1 corresponds to omega equal to 0. Same way when z is equal to minus 1, this is equal to 1 by 2, 1. When you substitute minus 1 here, you can see 1 plus 1, that's equal to 2 by 2, that's equal to. So now you can see this is allowing the high frequencies to pass but rejecting the low frequency. So you can say this is indeed a high pass filter. This is indeed a high pass. All right. Now example of a band stop filter. Example of a band stop filter. Example of band pass. Let's do band pass filter first. Band pass filter. Now we can obtain a band pass filter by combining a low pass and high pass filter. This is very simple. Now, so impulse response of this will be simply 1 by 2. Let me if I remember 1 comma 0 comma minus 1. Please check it. Please check this whether this is band pass. Alright. Please verify it yourself. And similarly, the example of band stop filter is h of m is equal to 1 by 2, 1 comma 0 comma. So you can obtain the z transform expression of this h of z is 1 by 2, 1 minus z is by minus 2. Similarly, the z transform expression of this will be 1. Right? So these are the band pass and band stop filters. Alright. So these are several examples of simple low pass filter. Alright. Now please obtain h of omega from here. Okay, h of omega and plot it. Right, plot it. We already done this several times. Please plot it and see this is indeed a low pass, high pass filter. Alright. Now what I want to do next, I want to obtain the difference equation expression of this. So you can write this is the difference equation expression of this will be, we know h of z is here, h of z is given as y of z by x of z, and this is equal to 1 by 2, 1 plus z inverse, rearranging the term, so this will be 1 by 2 x of z plus z inverse x of z. Now taking the inverse z transform, you will obtain y of m is equal to 1 by 2 x of m plus the z inverse z transform of this, it will be x of m. So this is the difference equation expression of a low pass filter. Same way, the difference equation expression of this and this will be h of z which is equal to yz by x of z is equal to 1 by 2, 1 minus z inverse. Rearranging these terms, we will get y of z will be equal to 1 by 2 x of z minus z inverse x of z, right? So taking inverse z transform, this will be y of m will be equal to x of m minus x of m. So this is the difference equation of high pass filter. So this is the difference equation of a high pass filter. So we can write it like this. So say y of m is 1 by 2 x of m minus x of m. So this is the difference equation of a high pass filter. Simple high pass FIR filter. Same way you can do it for these two. So let me do it for band pass filter. Let me do it for band pass filter. H of z, sorry, h of z is equal to 1 by 2, 1 minus z to the power minus 2. So h of z by xz, that will be equal to 1 by 2, 1 minus z to the power minus 2. Rearranging the terms, we get y of z is 1 by 2 x of z minus z to the power minus 2 x of, right? So this will be equal to 1, taking the inverse Z transform, this will be y of n is 1 by 2 x of n minus x of n minus 2. What I'm doing actually here, I'm using the shifting property of Z transform. Same way, the Z transform of band stop filter, which is given by h of Z is equal to 1 by 2, 1 plus Z from minus 2, will be given by y of Z by x of Z is 1 by 2, 1 plus Z from minus 2. We can write it like this. So we can obtain the y of n from this by taking the inverse Z transform. Will be x of n plus x of n minus 2. Right? So these are the different equations of this simple FIR low pass filter. Now in the next session, what we'll do, we'll design an FIR filter. We'll design an FIR filter, right? And we'll write the steps. What are the different steps required to design an FIR filter? All right, let me end the session here. Please plot the high pass, low pass, and response of these in MATLAB. Okay, how will you do that? Substitute here. Substitute here z equal to e raised to j omega, and do that. Okay, do that. That's it. All right, let me end the session here.